Hi everyone, I'm Mourjo from HelpShift. I work in the backend team at HelpShift, and my talk is about writing a framework to provide a way to run maintenance tasks that on the data that we have at HelpShift. So I know it's late, and I know probably many of you are hungry, and I promise you at the end of this talk there is some food. But during this talk, I'll try to give you some food for thought. So just to start off, what is HelpShift? HelpShift is a platform which provides a means of communication between users or customers and brands. So it is possible by integrating HelpShift into your product. Your users or your customers can reach out to you if you're making a product and start a conversation with you. And in the last 1 year, we saw that there were more than 150 million such conversations that were carried out on HelpShift. Now, this is a large number, but the vastness of this number really comes into the picture when you think of running some maintenance on each of these conversations. So let's take one such maintenance job that we have to run. Suppose tomorrow we want to release a feature where we want to segment conversations into buckets. So let's say that from tomorrow onwards, when you open your HelpShift platform, there'll be a segment for each conversation that was ever had on HelpShift. So because this is not there in production right now, we will have to go through all the conversations that is there currently, add a default property to each of the conversation, which is going to be a bucket on which this conversation is going to be segmented on. And therefore, the need arises to scan through all of the 150 million conversations that are there and to add some more data onto it. Now, this is a daunting task as it is because we are scrolling through such a large data set. But what becomes even more challenging is that the distribution of this data across our customers is non-uniform, meaning that there are some customers which have more data than the rest, and there are many customers which have less than our top customers. So this led us to some roadblocks while running maintenance tasks at HelpShift. And the first roadblock was that some jobs would take a really long time to finish, an arbitrarily long time to finish. And then there were some jobs which were hand curated and made to work fast, but it was not extensible. So it would only work for that job, but not for any other jobs that were written in future. So what we wanted to achieve by writing a framework was to make sure that all jobs that run on HelpShift finish fast and have some other guarantees that we want to have for every single job that runs on HelpShift going forward. So the goals that we wanted to achieve with our framework was that the jobs that run on this framework should be fair. And what I mean by fair is that it should be fair to the person who's running the job, meaning that if there is an X amount of data in total on HelpShift, the running time of the job should only depend on the amount of data that the job needs to handle. And it should not depend on how the data is distributed. So if 90% of the data is with a few customers and the rest of the data is there for the 90% of the customers, that should not cause the job to run really long. It should only depend on the amount of data in total and not how it is distributed across customers. And the second requirement that we had was that the job framework itself should be easy. And this follows from the founding principles of Clojure that if we have something simple that is made easy, it will be accepted widely, right? So if someone joins our team and we want to write a new job, using this framework should not be a very difficult task. And writing a job on this framework should be easy enough that it attracts more people to use this framework very easily. So with these goals in mind, let's look at what is the first approach that we can take to achieve this goal. So the first approach that we can think of is that, let's say we have a few processors which will process each customer, and these processors are just functions executing on a thread pool. And what this function does is that it takes one customer, processes it by running the maintenance job for that customer. Once it finishes, it goes on to the next customer and then the next, and until there are no more customers remaining. So what we are doing is that each process is a thread on a thread pool, which takes a customer, runs the job from start to finish for that customer, and goes on to the next. Now, the problem with this approach is that some customers, as we showed before, have more data than the rest. So ultimately, after a while, what we might end up with is that there are only a few threads active, and the rest have finished. And so the targeted parallelism that we wanted to start off with is not achieved. So some processors are not doing any work because they don't have any more work to do. So this approach is easy to understand, and it is very important that we have achieved the requirement of being easy, but the problem that we are having with this is that the way the data is distributed becomes a factor in how long the job runs. So if all the data is concentrated with a few customers, we might end up with a longer time than if we were able to distribute it all across uniformly. So how do we solve this problem, right? We know that there are some customers which have more data, but we want to be able to go above that data distribution. So let's say the problem here is that some customers have more data. Now, what if we try to say that we are not going to look at customers as a whole, but we are going to split customers' data into smaller parts, smaller, more granular tasks rather than one big chunk of entire customer's data. So that is what the second approach is about, where we are not submitting entire customers' data as a task for our threads to execute, but we are saying that now we are going to say that it is not one customer that you have to execute at once, it is just a segment of my customer data. So one possible way of dividing a customer's data is to do it by months, so because it's easier to understand. So let's say that we are splitting each customer into months, so January, February for one customer, and January, February for the next customer, and so on. So now what happens is that after a while, when the smaller customer's job is finished, we are only left with a few big customers, but even then, because we have split the big customers' data into smaller parts, we are able to harness the power of all our parallel threads that are working, and they are still executing in parallel, so the throughput of the system is better than what we saw before. So what we are actually doing here is that we are taking our entire customer's data, we are taking each customer's data and splitting it up into parts. And these parts are going to become our unit of execution that are handled concurrently. So we split our customer's data into months, and we say that each month is now going to be processed on in parallel. Now this is well and good. This is better than the previous solution, that if one or two customers are the only ones who are executing, we are still able to process it in parallel. But there are some nuances that we want to point out here. So if you look at some of the chunks that we divided our customers' data into, some of them are not of the same size. And there are some chunks which have more data, and there are some chunks which have very less data. And this happens because we are splitting our data into time ranges, but we don't know how much data is there in each month. It might be possible that the month of January has a lot more data than the rest of the months of the year. Conversely, it is also possible that some months may not even have data, but we don't know that in this solution. So although this job is mostly fair, assuming that in the limiting case, we will have mostly uniform data, it is still easy to understand because we are splitting the input and saying that we are just splitting it by time ranges. It's still easy to use, but we are missing something here. And what we are missing is that although the uneven distribution of data across our customers is handled by splitting it into parts, what we have introduced is that the way we are dividing the task is itself not uniform. So some months have more data, some months have less data, and that can affect the performance of the job. So at this point, let us introduce a new goal that we want to achieve, is that we want to rise above the distribution of the data inside a customer's domain. So suppose we have all of our biggest customers' data in 1 month. We don't want our job to sacrifice the amount of performance it can give just because the data is not as we expect it to be. So can we achieve robustness in the sense that we are going to handle all kinds of data distribution, and still achieve the goals that we set out to achieve? So what can we do here? So what we are doing right now is that we are splitting a customer's data into different chunks, and these chunks may or may not be of the same size. Now we can hope that these chunks are going to be of the same size, but they may not be even. Also, it is possible that we are splitting too much, right? There are some customers which don't even have enough data, and we are still splitting it into months. And maybe most of the months don't even have any data in them. So what can we do to solve this? The ideal solution would be not to split it according to date ranges, but to split it in such a way that the amount of work that we have to do for each chunk is the same. So uniform division, so that the amount of work that needs to be done is constant. So the problem that we have with the second approach is that we are splitting the data before looking at what the data is. So we are saying that we are going to divide it into months, but we don't know how much data is there for the month of January or February. So this gives rise to this situation where we might end up with some pockets of more data, some with very few data. And the way that we propose to solve this is to decouple the data collection from the execution of the task. So when we say that we are going to split it into months, we don't know how much data there is. But what if we could say that, okay, now we have fetched the data for January, but we see that January has too much of data and this needs to be split further. And once we have done that, we would be able to decouple the execution so that the final processing of the job happens on uniformly sized tasks. So that brings us to our final solution that exactly does this thing. So here what we are doing is that we are splitting our data collection from our workers into two parts, which are called the iterators and the workers. Just like before, they're also executing on thread pools. And these are parallel processes communicating through in between a channel. So what does an iterator do? An iterator takes a task, a coarse-grained task, and it looks at the data and decides whether it needs to split it up into further parts or not. Note that the iterator doesn't actually do any work. It just makes the data ready for the final layer which actually works on the data. And that is our workers, which will take what is given to it from the iterator and process those tasks instead of processing the tasks that were given to the job as a whole. So let's see how that all fits together. So as before, let's say that we are giving the same data to the task framework as before. So we have customers and months. And now what the iterator, each of these tasks are given to our iterators. And what does the iterator do? It just calls a database and says that for this month, for this customer, give me the next 10,000 records, for example. And they can do this over using the primary key or some index to make it as fast as possible. But the iterator's job is just to collect the data and to package it in a way that the worker can execute on. So once the iterator has the data for, say, a batch, it can chunk the data into equal-sized entities. So let's say our workers are only going to work on 100 entities at a time. The iterator now can split those 10,000 records which were fetched and package them into chunks of 1,000. And therefore, when the worker finally gets the task, this is the worker is the function that actually runs the maintenance that we wanted to run. So now the worker gets only 100 or 1,000 units of work which was given to it by the iterator. So we are not going to run into a situation that if January has a lot of data, my worker is stuck with just processing January for too long, because there is a level of indirection in between which splits, which decouples the data arrangement from the execution of the task on the data. Now it is possible that some of our iterators may finish before other iterators. And that goes back to our original slide where some customers have more data, so it takes longer for them to finish, but that is fine. And that is fine because the iterator doesn't actually do the work. It just fetches the data, repackages it, and submits it to a channel on which the workers are working on. So as long as the iterators are fast enough and can query the database fast enough, all our workers are going to be kept busy, and the throughput of the system is not going to be compromised. So this framework can be divided into three sections. The first is the launcher that announces what is my iterator and what is my worker. And between the iterator and the worker, we have a channel which is the meeting point between the iterators and the workers. So my iterator thread pool can be as big as my machine would allow, and my worker thread pool can also be as big as my machine allows. But the point of synchronization, the point of contact between these two is a co-racing channel. And this is important because now our two iterator and worker phases are completely decoupled. The only thing is that if the workers are too busy, by back pressure through channels, the iterators will slow down, and the workers, on the other hand, will be able to go as fast as our iterators allow. So the throughput of the system never sees the inconsistency, the non-symmetrical data that is actually there in the database because of this iterator layer. So let us look at how this looks in code. So suppose you're writing a job using this framework. First, we write a launcher which announces to us that there is the iterator function, there is the worker function, and there are the tasks that the job gets as a whole. That is going to be our months of data for each customer. Once we have announced this, we write the iterator function. The iterator function does exactly what we set out to achieve. That is, it will fetch data batch by batch. And once it has a batch of data, it can start pushing the data into a channel into equal-sized units of work. And once we have done that, this data that we have pushed onto the channel is sent to our worker function, which was also announced by our launcher. And the worker function does just what we wanted it to do. It will take a chunk, a uniformly divided chunk of work, and perform the actual maintenance on it. So this job is fair. And why is this fair? Because even though the data is distributed across customers and the time ranges, the value of the amount of data per unit time is not constant, we are able to rise above that inconsistency in the data, and the final working worker layer never sees those inconsistencies, and the runtime of the job is not dependent on the data distribution. It is easy to understand this job because all you have to do to write a job in this framework is to have two functions, and these two functions are your iterators and workers. And with the help of core async and closures primitives, it's really easy to write these functions and pass it on to the job. And finally, it is robust also, because if there are some data points that have a lot of data, we are not ever going to get slowed down because of these spikes in data. For example, let's say there is a lot of holiday wishes during the holiday season in December, but that is not going to affect the throughput of the job because the workers are always seeing same sized units of work which are happening in parallel. So concurrency, as defined by Rob Pike, is a design choice, and what we get out of it is parallelism. So parallelism is just the outcome of a good concurrent design. And with core async and closure, what we are achieving is that we are communicating. We have communicating processes with a channel in the middle. So if I am running my job on a very strong system, we can have as many threads as we want for our iterators and workers, and it still works. On the other hand, if you have a very simple job which just runs on a very small server, we can have one thread for the producer, one thread for the iterator, and one thread for the worker, and it still works. So with Clojure, we are able to harness this kind of power of concurrency very easily. And that is something that we want to emphasize on, because in the founding principles of Clojure is to make things easy, make powerful things easily accessible. And I think we have been able to do that with this framework. If you like what I talked about today, come say hi to any of us at HelpShift, because we are hiring and we are doing a lot cool stuff like this. You can hit up this URL to see the jobs that we are hiring for. Questions?
So how did you come up with that number of 10K records? Just wanted to just.
Yeah, so the 10K records is arbitrary. So, and that is because when you define your iterator function, you define how you iterate through your data. So you're just submitting that function to our framework, and you choose how you batch your data. So 10K records works for one of our data sets, but you might have some better results depending on your data set. So it's all on the person who's running the job. It's not fixed. 10K is just because we have 150 million records. 10K was a good small unit of work.
Shouldn't it be dependent on like across all the months for a customer? What is the minimum data is available, right? Like for a customer, you have in a month, right? So if there is a there is a minimum amount of data for that customer across all the months, that should be the minimum size of the data set, right?
Yeah, that's
And then
true.
you can actually do
That's
that.
true. But we have multiple data sets, as you might do too. So it depends really on what job you're trying to achieve in the end and how the data for that job is distributed. So the control is really on the person who's writing the job. We are here only talking about the framework. So framework gives you this this configurable parameter as to how much you want to batch or how little or how big you want to batch it.
Thanks.
Hello. So, in your iterator, so are you considering the homogeneous data storage, or it can be, I mean, any sort of, I mean, different kind of data source you can, I mean, do your framework handle that, or I mean, the task writer will decide on that? So that part I am not clear about.
If I understand correctly, you want to know how the data is iterated.
Yeah.
Right.
So from different kind of non-homogeneous data sources.
Okay. Okay. So the iterator is just a function, right? It's a closure function, right? And if you have multiple data sources that you're taking data from, you can incorporate the logic into that function that you're submitting to the framework. So you can have multiple layers of queries that you have to do before you can say that my task is ready for processing. So that really depends on how you package your data inside the custom iteration function. So if you have like say 3 data stores and you have to get data from all these 3 stores before you can perform the task on it, you can do it on the iterator level, saying that I'll query all my data stores first, get all the data, batch it together, and then proceed to the workers.
Okay. Got it. Yeah, thank you.
Any other questions? I think we're good.
Thank you.